In case you were not aware, a foreign object named 3I Atlas entered our solar system and was first spotted in July 2025. It created and is still creating a lot of buzz because of some of its characteristics, to the point that many people, even in academia, started to consider the possibility that the object could be a massive spacecraft. I suggest you do your own research on 3I Atlas, as there is already a plethora of resources dealing with this object, and since the purpose of this video is not to talk specifically about 3I Atlas, but to merely use it as a pretext to discuss plasma propulsion for interstellar travel. Right off the bat, let's be clear on the assumptions. We will be assuming that 3I Atlas is real, and its impressive reported characteristics, while still up for debate, are relatively close to reality. These are important assumptions, just like assuming the Earth is spherical while all your senses tell you that it is flat. It is probably safe to say that just like 99.99% of humans have never observed directly the planet from space, 99.99% of humans have not observed 3I Atlas directly with their own eyes. For all you know, this story about a strange asteroid could be entirely made up, although it seems very improbable someone will have the financial resources to manufacture such a fake news on a large scale. The point here is not about truth or trust, but about working with assumptions. While we are at it, let's also make a bolder assumption about 3I Atlas. It is a spacecraft. It results from these assumptions that 3I Atlas is the fastest interstellar spacecraft ever observed, traveling at a speed of 230,000 km per hour when it was first spotted. As 3I Atlas approaches the Sun, its velocity could peak at 250,000 km per hour, if it is to behave like a normal comet or asteroid. But for the purpose of our discussion, let's assume that the cruise speed of the 3I Atlas spacecraft remains constant at its hyperbolic excess velocity of 210,000 km per hour during its interstellar journey, which is the calculated speed it will retain far from the Sun if, again, it were to behave like a real comet. To put things into perspective, the current speed of the fastest man-made interstellar probe, Voyager 1, is about 60,000 km per hour. Voyager 1 was launched in 1977, and its current speed, far from the Sun, is close to its hyperbolic excess velocity, in the absence of further acceleration. The closest star to the Sun is Proxima Centauri, which is 4.2 light-years away. If 3I Atlas had originated from Proxima Centauri, it would have taken it over 20,000 years to reach us. Possible? Sure. Plausible? Not really. If Voyager 1 was headed towards Proxima Centauri, it would take it close to 75,000 years to get there. Of course, we know Voyager 1 is not headed towards Proxima Centauri, just like we know 3I Atlas's trajectory is not compatible with a Proxima Centauri origin, unless the spacecraft made some elaborate maneuvers before allowing it to be observed from the Earth. What if 3I Atlas actually originated from a base located in the Oort cloud that orbits very far from the Sun, well beyond Pluto's orbit? The outer region of the Oort cloud is estimated to be between 1.5 trillion and 15 trillion kilometers away from the Sun. To reach us from there, 3I Atlas has to travel 800 to 8,000 years, still a little bit far-fetched. The inner region of the Oort cloud is estimated to be between 300 billion and 500 billion kilometers away. To reach us from there, 3I Atlas has to travel 150 to 300 years. Now it starts to become more reasonable for a human brain. Still, can we make this a tad more accessible to the skeptical but open minds? Well, according to the latest data, astronomers have estimated that there could be a massive and yet undiscovered ninth planet orbiting the Sun between 45 billion and 75 billion kilometers away. If 3I Atlas came from this hypothetical planet, it would take it between 25 and 40 years to travel to the Sun. That's within a human lifetime, for some alien or not so alien breakaway civilization. Some minds, with a more eccentric orbit, have associated this hypothetical ninth planet to Planet X, also known as Nibiru. For those minds, it is interesting to note that 25 to 40 years will bring us back to after some interesting events, like the first atomic detonations, the Roswell incident, or the launch of Project Oumuamua, precursor to the SETI program. Given that its speed is only 3.5 times faster than that of Voyager 1, 3I Atlas does not seem to rely on some exotic propulsion systems. So what could that propulsion system be? But before we leave the Earth's atmosphere, in the second part of this video, press the like and subscribe buttons now, as you might not get another chance before we return home. While 3I Atlas's speed of 210,000 km per hour seems almost underwhelming in the immensity of the interstellar void, if an object was traveling at that speed in the Earth's atmosphere, it would be immediately categorized as a UFO or UAP, flying close to Mach 200. That's about 20 times faster than Russia's battle-tested hypersonic missiles Kinzhal or Rezhnik, flying at Mach 10, or only 7 times faster than the fastest hypersonic missile, the Secretive Avangard, flying at Mach 27. Believe it or not, humans already know how to achieve Mach 200 in the Earth's atmosphere. The technology is called magnetohydrodynamics, also known as MHD. I have talked about electrohydrodynamics or MHD propulsion in previous videos. I suggest you watch them if you are not familiar with this technology. The difference between MHD and MHD is that MHD relies on the strength of an electric field applied to a plasma, while MHD makes use of a magnetic field to accelerate the plasma and produce thrust. Most of the non-classified research and development on MHD for propulsion systems is focused on MHD thrusters, also called magnetoplasma dynamic thrusters. Typically, those thrusters are dedicated to space missions and can theoretically allow a spacecraft to attain very high velocities. In the Earth's atmosphere, hypersonic velocities are usually achieved with thrust provided by solid propellant rocket engines instead of MHD thrusters. But as previously mentioned, humans already know how to make use of MHD to attain hypersonic velocities in the Earth's atmosphere since at least the late 1970s. Actually, MHD permits not only hypersonic velocities in the atmosphere, but also quasi-instantaneous acceleration and change of direction, while enabling silent motion, as the technology requires no moving parts. Today, MHD levitation and hypersonic motion in the atmosphere is not a scientific question, but a technological one. The basic principle is to essentially ionize the air around the aircraft and move the aircraft in a frictionless manner with a magnetic force within the surrounding generated plasma. For this, two main technological challenges must be overcome. The first challenge is the energy source. It must produce sufficient energy to ionize the air around the aircraft and to generate a powerful magnetic field to force the motion of the plasma in the desired directions. A nuclear reactor will do the job. As a matter of fact, nuclear reactors currently already power today's state-of-the-art submarines and aircraft carriers. Under the water or on the water, the weight constraint is not an issue, and proper shielding can be engineered to protect crew members against the radiations from the onboard nuclear power plant. In the atmosphere, shielding against radiations from the nuclear reactor will be too prohibitive from a weight constraint standpoint. That is not to say that nuclear power engines have not yet been deployed in the air. Russia is currently testing a cruise missile named Burevestnik, which is powered by a nuclear reactor which allows the missile to remain almost indefinitely in the air before striking a target anywhere on the planet. The cruise missile is equipped with a nuclear warhead, so it can be presumed that its intended use is for a doomsday scenario, which made the life of the Russian engineers a little easier, since they did not have to worry too much about the radiations emitted by the nuclear reactor as the missile circles the globe before its final dive. Nevertheless, the Burevestnik shows that the energy source issue for MHD propulsion in the atmosphere has been resolved, based solely on information publicly available. The fact that the US had a similar project, codenamed Pluto, back in 1957, tend to indicate that this technology has probably been harnessed for a couple of decades already. The second challenge is to engineer powerful magnets capable of producing strong magnetic fields from the energy produced by the nuclear reactor, while keeping the dimensions and weight of the magnets compatible with the constraints of an aircraft. Back in June 2024, high-temperature superconducting magnets have been successfully used by China for fusion energy. Work is currently being done on miniaturizing high-temperature superconducting magnets for space travel. Have humans managed to put all these different technologies together in classified projects to produce MHD-propelled aircraft capable of reaching hypersonic velocities in the Earth's atmosphere? What seems to be logical is that once this technology has been successfully deployed in the Earth's atmosphere, adapting it for interstellar travel should not be that much of a big deal, given the absence of weight constraint in space. Friction is also much less of a concern. One issue could be the insufficient density of ionized particles in regions of space that are relatively empty. So an MHD-propelled spacecraft must still carry some level of propellant reserve to generate a plasma envelope around it. An alternative to bringing vast quantities of propellant to space, notably for long-duration travel, could be to colonize an asteroid and equip it with a couple of nuclear reactors and giant magnets. The natural resources on the asteroid, like water or carbon dioxide, would provide the materials for the plasma production to steer, accelerate, or decelerate the asteroid during its journey through space.